good afternoon, everyone. If anybody is sleeping, please raise your hand. Nobody. That's good. Yeah, before we start on this topic, so just want to remind you guys that in your your name tag there's a QR code, there's a survey. Please try to fill the survey if possible. Okay, my name is Sean Yu, and I'm in this power electronic industry for 19 years. I'm really happy to be here to present you this topic. Okay. In this section, I'm going to present a topic of phase shift full bridge converter, which is very popular in the high voltage isolated DC-DC converter. And I'm going through some fundamental of this phase shift full bridge converter as an introduction, for the very detailed. So we have a call to action, like a lot of paper and presentation materials that after this one you can go check. Okay, so here's today's agenda. So first we'll go through why we want to use a phase shift full bridge converter in your design, and first of all we want to see what's the application that is this phase shift full bridge converter is suitable for. And then we are going to talk about when you design a phase shift full bridge converter, what's the design considerations, and how it achieves source switching, and also different type of output rectifier that you can use in a phase shift full bridge converter, voltage spike under output rectifier, and how you clamp those voltage spikes, and different control method for the phase shift full bridge converter, and different mode of synchronous rectifier control you can use. And also we're going to talk about light load management, how you manage light load for phase shift full bridge converter, and then we'll introduce a design example and followed by a summary. Okay, so before we talk about phase shift full bridge converter, so first question you ask yourself is, why should I choose phase shift full bridge converter in my design, right? So here's a trend we see in general in a power supply. So we see there's a need to design there's a demand to have your power supply design going smaller and lighter in weight, and to have a higher efficiency. So on the right hand side is an example of a server server system that they measure the energy efficiency, use power use efficiency, PUE. This number, PUE number. So if the PUE number is low, meaning the most of the power, input power, does go into the load you want to use. Like for example, in server it's a CPU, GPU, those kind of load. Instead of spending a lot of energy in cooling and other stuff, right? So that means when we design a power supply, we need to design have a higher efficiency. And then second thing is there's EV application, EV HEV application, that the weight is money. So if you can design your power supply to have lighter weight to minimize the transformer size, then basically your car can run more efficiently, right? So that's one trend. And the other trend is that there are for example 80 plus certification, and they are in several application. There's an open compute project committee that have for example, in this example, we have 80 plus titanium, and also the OCP standard called MCRPS that define what's the efficiency number you need to meet in order to get certified in these certifications. So those are the two requirements we see, right? So size, power density, and weight that we want to reduce. And so phase shift full bridge converter is one of self-switching converter. So then why we want to choose why we want to use self-switching, especially in high voltage application. A lot of design that we will have input voltage at around 400 volt. So in such application, the switching. So if we are doing a hot switching, then you will see the voltage and the current overlap, and then you will have a switching loss. And if your voltage is very high, right? For example, like at 400 volt, the portion of the switching loss compared to the conduction loss will probably be equal. While in maybe in 48 volt system, the switching loss is less significant than high voltage system. So in high voltage system, there is a benefit that people want to go to a self switching, right? So and the other thing is when we are at the hot switching, so basically if you can switch turn it down faster to minimize the crossover section, then you are able to lower your switching loss, but then you will result in EMI issue because of high DVDT in your system, right? So there will be a trade-off, to be more efficient or to be less EMI. So if we do self-switching turn-on, so basically self-switching turn-on means zero voltage switching. So what is zero voltage switching? Meaning, so say this is a MOSFET voltage. So if you can allow your MOSFET voltage going down to zero before you even turning on the FET, then we can achieve self-switching. We can achieve zero voltage switching, right? So how do we achieve that? Basically, we need to apply a negative current to be able to discharge the output capacitance of the FET, so that we can fully discharge the output capacitance voltage down to zero. Then they will allow us to have a zero voltage on the drain to source voltage before we turn on the FET. So basically, we need a circulating current to do that. Okay, so I just on the right hand side is a full bridge converter. So in a full bridge converter, you can have a different control method, different operations. So basically, you can either operate it as a hot switching full bridge, or you can operate it as a phase shift full bridge. So hot switching full bridge, you got the switching loss, at this circle area, and phase shift full bridge, basically we use this negative current to discharge the VDS voltage down to zero before we even turn it on. And if we have a self-switching, we are able to eliminate the turn-on switch loss, and therefore it allows us to switch at a higher frequency than the hot switching converter. So phase shift full bridge converter is not the only self-switching isolated self-switching converter that people are using. The other popular topology that people are using, and which is also self-switching converter, is the LLC resonant. So basically, the main difference between the phase shift full bridge converter and LLC is basically the phase shift full bridge converter relies on the series inductor and output inductor. The energy is stored in those two inductors to charge and discharge the output capacitor of the FET to achieve self-switching. While the LLC converter relies mainly on the magnetizing inductance to store the energy and to discharge and charge the COSS on the MOSFET. Okay, and the LLC converter basically is how you do regulation is changing the frequency, then the input to output voltage gain will change so that you can do output voltage regulation. while the phase shift full bridge converter is um, by varying the phase difference between the two legs to control the duty of the transformer winding, so that they can you can use that to regulate the output voltage. So in generally speaking, phase shift full bridge converter is easy to have phase change response than LLC, and usually it's good for wide input to output voltage range operation, and the frequency can be fixed. Unlike the LLC, the frequency is changing all the time. But the drawback of the phase shift full bridge converter is, if the output rectifier is not the self switching. So LC converter, if your switching frequency is lower than the series resonant frequency, the output rectifier will also able to achieve a self switching, while the phase shift full bridge converter output rectifier is not self switching. So if there is a reverse recovery charge on the output diode, they will introduce additional loss on the phase shift full bridge converter. And also the other thing is because we are relying on the energy stored in LS and LO. So the energy stored in LS and LO depends on the current through this inductor, right? So if the current is controlled by the load. If the load is lighter, the current will be lower, then the energy stored in the inductor will be less. So it's easy, there's a chance that the phase shift full bridge converter can lose self switching of its one leg at lighter load. The other popular topology in higher power application, maybe multi-kilowatt, is the dual active bridge. So dual active bridge is very, very similar to the phase shift full bridge, but instead of phase shift full bridge have a phase difference between the two half bridge on the primary side, the dual active bridge have a phase difference between the primary side winding and secondary side winding, and and the output regulation and the power, the total power being transferred is controlled by the phase angle between those two phase difference on the between primary and secondary side windings. So usually we will see that because one thing you can notice that there's no output inductor for the DAB, so you can expect the DAB have more output voltage, more ripple at the output, right? And the other thing is for DAB, so this is to control the phase difference between primary and secondary windings. Is we call like a one phase control, right? So then under one phase control, there's you can see a lot of circulating current through on the resonance stage, and that will causing a lot of losses. So it's possible to apply a multiple phase phase control. So instead of only have the phase difference between primary winding and secondary winding, you can also including the phase difference between the primary two legs to minimize the circulating current. But as you can imagine, by doing so, the control complexity will be very high. It will be pretty challenging to control. So we today's topic is talking about phase shift full bridge. So what the application that is good for phase shift full bridge? So here is one example. So previously I mentioned that the phase shift full bridge can achieve a very fast transient response. So in server application, in the past, so server load is basically CPU, but now we are having a GPU, and so GPU from NVIDIA. So some of those GPU load are not very friendly to our power supply. So in the past, CPU load we just for this AC to 12 volt output, the CPU load probably have a low tension around like 2.5 amp per microsecond through rate. But GPU load, we have seen some people asking for like 10 amp 10 amp per microsecond here. So it's really tough for us to meet that requirement and meet the output voltage regulation under this load. But it's proof that phase shift full bridge converter is able to do that. And the other application is I also mentioned that phase shift full bridge converter is good for wide input and output range application. So for example, in EV, there's a high voltage battery, and also there's a need to convert the power from high voltage battery to low voltage battery. So in this case, both input and output voltage are pretty wide. So if you want to use LC resonant converter in this application, then to cover this input and output voltage range, you will need to design your transformer to resonant inductance have a very low ratio, which will result in a high circulating current and low efficiency. But as a phase shift full bridge converter, use a different component for the sub-switching, so you don't have that low efficiency issue in this kind of wide input-output application. Okay, so let's talk about the sub-switching and operation of phase shift full bridge converter. So how does phase shift full bridge work, right? So basically, on the right-hand side, you can see the PWM signal. So this is leg 1 here, and this is PWM signal on the leg 2, right? So basically, what we are trying to do is we're trying to make a phase difference between the leg 1 and leg 2, and because of that phase difference, if for example if like two blue is high side and purple is also high side. If two high sides on, right? If two high side fed are on, so basically we are applying no voltage to the transformer winding, and we are only apply voltage to the transformer winding when a diagonal pair switch is turned on, right? So basically you can by using the phase difference between two legs to control the how much duty you want on the transformer windings, right? So on the primary side, we can create this kind of pulsating waveform, and then if through the transformer it convert to the secondary side. On the secondary side, we are using this waveform through the diode and the inductor to form a operation like a buck converter, right? Then you can basically regulate your output voltage by control the duty cycle here. So one thing you can notice that is even though on the primary side the voltage is non-zero here, but when you transfer to secondary side, it's zero voltage here. That is because when we apply say so there's a transition, like when the current changing direction, the voltage will fully apply to the series inductor. At that period, the secondary side voltage will be zero. So that means if your inductor is large, this duration will increase, which we call it the duty cycle loss. So if you have a large inductor, meaning you have a larger duty cycle loss, and meaning the controllable output range will reduce. So that's a trade-off, in your design. So if you have a larger inductor, it's easy to achieve self-switching over the full range, but it's you have more duty cycle load. So there will be a trade-off between the self-switching range and the operation range, the output voltage regulation range. Okay, so basically how I mentioned that before, right? So how we achieve self-switching is basically in both LLC or phase shift full bridge is the same. We need to allow a freewheeling current at the fed switching transition. There's already current at the right direction, able to use to discharge and charge the COSS, so that we can achieve self-switching. So let's look at the waveform one by one. So in leg one, you can notice that the current here, right? We use this current to change, this current to discharge the COSS during the leg one switching transition, and you can see this current compared to the other switching transition is lower. Basically, this current is the it's the output inductor current, the ripple of output. So basically the how do you say, the average output current minus its ripple. So it's the value at the current value at this point is lower. So it's basically easier to lose ZVS, and so at this transition, we are basically only mainly rely on the energy stored in the LS to achieve ZVS. So at the other switching transition, as you can see on the waveform, the current is basically the output current plus the output inductor current ripple. So we have more energy during this transition to charge and discharge the COSS. So it's it's easy to lose ZVS at leg one, while it's easy to maintain ZVS at leg two because of the naturally the current and the switching transition between these two legs are different. Okay, so let's talk about the rectifier that used in this phase shift full bridge converter. So basically, there are three types of commonly used rectifier for phase shift full bridge converter. They are full bridge rectifier, and center tap rectifier, and current doubler rectifier. So let's go through the operation of loss rectifier one, quickly. So when let me see. So when VAB is positive, so we are also apply the positive voltage to the positive negative voltage here to the second winding. So for full bridge rectifier, there will be this diagonal pair conducting current, and in center tap there will be one of the output winding conducting current through the inductor, and for current doubler it will be only one inductor conducting current through the output winding and diode. So when the VAB voltage is negative, then for full bridge rectifier, it will conduct current through the other diagonal pair, and for current doubler, you will conduct current through the other winding. While in current doubler, the current will be conducted through the other output inductor. So if you compare those three rectifier, you can notice that in both full bridge and the center tap rectifier topology, the output inductor frequency basically is doubled of the input, the switching frequency on the primary side. okay? And the current doubler switching frequency will be the same as the primary side switching frequency. So and also instead of this frequency is double, so the duty cycle of the output inductor can go to 100%, while the current doubler here, the maximum duty cycle can only go to 50%. So there are some trade-offs between different rectifiers, so it depends on your need. So here is just a table to compare the difference between those three rectifiers. Okay, so one thing is worth to mention is the voltage spike on the output rectifier of phase shift full bridge converter. So in this simulation waveform, basically we are only modeling the series inductor LS and also the output COSS, so rectifier COSS on the output rectifier. So if we don't have any clamping circuit or snubber to clamp the voltage, there will be a ringing, oscillation between formed by the LS and the COSS. And if there's no clamping circuit, those voltage can be 2 times, of the input voltage and times the turns ratio on the output rectifier. So I mean, in this model, only COSS and LS are modeled. If you consider your rectifier body dial has a reverse recovery, this voltage will only go higher, right? So basically, if we want to design an efficient power supply to use lower RDS on synchronous rectifier FET, then we must try find a way to limit the spike so that we can use low RDS on to reduce the SR total loss, conduction loss, right? So first try, and is probably most general usage is this passive snubber. So basically, you can add the RCD snubber, from the connect, at the front of the output inductor, output and the ground, right? So basically, the output voltage, the SR rectifier output voltage, will be clamped through the diode to this capacitor voltage. And how high the capacitor voltage will be is depends on this resistor value. So basically, the resistor value and the power dissipated on that resistor can be calculated through this equation. But in short, if we apply a smaller value of resistor, we are able to lower the clamping voltage, lower the rectifier voltage stress, but the power loss will just increase. So there's a trade-off between power loss and the voltage spike. So the other approach that people generally use for phase shift full bridge is the primary side clamp. So basically,